Welcome everyone. Today, we're going to talk about a massive breakthrough in how large language models process information, Doc-to-LoRA, or D2L for short. This technology bridges the critical gap between the blazing speed of prompting and the incredible efficiency of fine-tuning, allowing AI models to instantly internalize context like never before. To understand why this is a big deal, we have to look at the LLM context dilemma. Right now, when we want an LLM to read a document, we usually just shove it into the prompt, a process called in-context learning. It's fast to adapt and highly convenient, but it comes with huge downsides. It's transient, response quality degrades on long texts, and it causes a massive KV cache memory explosion that totally kills your latency. The alternative is context distillation, or fine-tuning, which bakes the knowledge permanently into the model's parameters. This gives you lightning-fast inference with low memory usage. But there's a huge catch: it is painfully slow, very expensive to train per prompt, and completely unusable if you need on-the-fly updates. This brings us to the Doc-to-LoRA paradigm shift. D2L combines the best of both worlds, the sheer convenience of prompting, with the operational efficiency of context distillation. How do we do it? We take a document and pass it through a lightweight D2L hypernetwork in a single forward pass. Instantly, this hypernetwork generates a context-specific LoRa adapter for your target LLM. Now, your target model can answer complex queries about that document perfectly, without keeping a single token of that document in its context window. Let's look under the hood at the architecture powering this. We start by feeding raw text documents into a frozen target LLM to extract variable length token activations. These activations are then funneled into our shared perceiver hypernetwork, which maps them into a fixed set of latent queries. These queries directly output our low-rank LoRa matrices. And here is the magic part: absolutely zero backpropagation is required to generate these weights. But what if your document is incredibly massive? We bypass native context limits using a chunking mechanism. We take that massive document and split it up, passing each chunk through the D2L hypernetwork independently to generate multiple LoRa adapters. Then, we simply combine them into a single, higher-rank LoRa adapter. This gives the model virtually infinite context capability, allowing it to generalize far beyond the lengths of its original training data without ever altering the hypernetwork's core output shape. You might be wondering, how did we train this hypernetwork in the first place? Through metalearning. We meta-trained D2L across millions of diverse contexts using query-independent distillation. Essentially, the hypernetwork learns a generic mapping to emulate the entire context distillation process in one go. We do this by minimizing the KL divergence between a teacher model that can actually see the context and a student model that only has our D2L LoRa adapter. This brilliantly bypasses the need to generate per-prompt queries and runs slow backpropagation when you're actually using the model. Let's look at the results, starting with flawless retrieval beyond base model limits. On a standard needle-in-a-haystack retrieval task, you can see the base model completely fails abruptly right after hitting its 8K native context limit. D2L, however, maintains near-perfect zero-shot accuracy all the way up to 40,000 tokens, or 40 chunks. And here is a real mind-bender for you: D2L achieves this incredible feat despite only seeing a maximum of 256 tokens during its training phase. And it does all of this while completely eradicating the KV cache explosion. Look at this graph of additional memory needed for inference. The base model using standard prompting rockets up to over 12 gigabytes of additional memory just to generate a response for a 128K token haystack. The D2L internalized model? It completely flatlines at less than 50 megabytes of memory, completely ignoring the length of the haystack. The takeaway here is huge: D2L entirely eliminates the memory tax of long contexts during inference. But we didn't just test synthetic tasks. D2L excels in real-world reading comprehension. Evaluated on rigorous benchmarks like squad, drop, and ropes, D2L universally outperforms standard in-parameter baselines like context distillation. In fact, it reaches about 82.5% of the absolute upper bound performance of full in-context learning. Crucially, it achieves this high-level performance with absolutely zero context tokens placed in the user's prompt. The true game changer, however, is sub-second update efficiency. Standard context distillation takes over 100 seconds and requires more than 40 gigabytes of VRAM to update a model. Doc-to-LoRA can complete the exact same internalization with less than 1 second of latency, and requires under 2 gigabytes of VRAM to update. This takeaway is massive. D2L finally brings the true power of context distillation to real-time, interactive, and on-device applications. D2L also demonstrates amazing zero-shot generalization on long documents. When we evaluated it on datasets like 2-wiki multi-hop QA, Casper, and multi-field QA, D2L handled documents up to 32,000 tokens long effortlessly, even though it was never trained on sequences longer than about 2,300 tokens. Because the context is successfully internalized, it drops the response generation memory from around 1 gigabyte down to less than 100 megabytes. Plus, our iterative LoRa generation uses 2 times less update memory than Oracle context distillation. Now, prepare to have your mind blown with emergent zero-shot visual transfer. We tested passing image activations from a visual language model directly into our D2L hypernetwork to generate LoRa weights for a standard, text-only target LLM. The result? The text-only model was able to classify images with 75.03% accuracy. The catch here is that the target LLM classifies these images purely through those internalized LoRa weights. Neither D2L nor the target LLM ever saw a single image during their training phases. D2L mapped these cross-modality activations entirely zero-shot. We also tested the hypernetwork's extreme generalization by internalizing the query itself. What happens if we invert the paradigm? We put the document directly into the standard context window, but we force D2L to internalize the user's query instead. Even though D2L was strictly trained to internalize factual knowledge from documents, it achieved a 0.587 Rugel recall score compared to just 0.185 for a baseline with no context. This completely proves the extreme robustness of our hypernetwork mapping. So, what are the practical deployment use cases for this technology? First, dynamic agents. D2L enables frequent, ultra-fast knowledge updates for agentic workflows reading active codebases or live data streams. Second, on-device personalization. It can capture evolving user preferences and chat history seamlessly with a microscopic memory footprint. Finally, persistent alignment. Developers can internalize safety instructions, system prompts, and formatting rules permanently, without burning precious context window budget on every single inference call. To summarize, the Doc-to-LoRA advantage boils down to 3 words: instant, infinite, and efficient. It's instant because it replaces massive backpropagation overhead with a single, sub-second forward pass. It's infinite because its chunking mechanisms seamlessly bypass native base model context limits. And it's highly efficient because it completely eradicates cache memory explosions during inference. Thank you for watching, and we invite you to explore the code and models at our GitHub repository.